Hello. In the last lecture, we were studying how Boltzmann started to establish the connection between entropy and probability. The way he did it in the beginning was to focus more on mechanical notions, but gradually his understanding of the term probability became more sophisticated, and the amount of mechanics that would enter into the argument would decrease while the amount of probability would increase. Of course, mechanics cannot be totally eliminated from the subject because, after all, we're talking physics here. So the quantities that you're talking about are energies and things like that. So some mechanics has to remain. So let us see remind ourselves what it is that he actually did. And so the idea was that he wanted a connection between the probabilities. The probability of a microstate is given by the exponential of the energy of all the particles plus some potential. At first, he did this by generalizing Maxwell's approach to just having velocities, the square of the velocities. He introduced first an external potential, and then he generalized this to all sorts of interactions. The way the connection to thermodynamics was made was by saying, well, the thermodynamic object is the internal energy, and we're going to take this as being the expected value of the Hamiltonian that appears here. And we're going to further say that any change in internal energy has to be given by a certain amount of work that comes from varying the parameters that enter here. For example, this guy here may depend on the volume. And so whatever changes in energy, in the expected energy you get from changes in these macroscopic parameters, you call that work. Whatever is left, you call that heat. And then energy, the entropy, the connection to entropy, is done by saying, well, the corresponding change in entropy when you go from one of these equilibrium states to another equilibrium state is going to be given by the heat exchanged divided by the temperature. So in this way, what he arrived at was a connection between entropy and the macroscopic variables that you use to describe a system, such as the energy, the volume, and so on. But you see, at this stage in the game, although there is a connection between the microscopic stuff here and the macroscopic stuff there, although there is that connection, the direct connection to probabilities had not yet been achieved. So this is more or less the state of the game around 1871. A few years later, around 1877, he comes back with an approach to entropy that is much, much more directly connected to probabilities. And the way he did it is by using combinatoric arguments. So the connection to probability comes from combinatorics. The idea was the following. You take phase space. So this is the single particle, the one particle, phase space. And you divide it in cells. The reason for dividing it in cells is that then you have discrete possibilities and you can figure out the number of possibilities, right? And so then once you divide it in cells, you figure out the number of particles that lie in cell 1, the number of particles in cell 2, the number of particles in cell 3, and so forth. And so you're going to describe the microstate, the microstate of the system, of the gas, is going to be described by saying which particle is in which cell. So specify the cell for each of the 10 to the 23 particles. And of course, in principle, you can make these cells as small as you want, right? So the macrostate now is a situation in which you have much less information. You just specified how many particles there are in cell 1, how many in cell 2, and so on, how many in cell M. Let's just say, yes, you keep going, and this one here is going to be the mth cell. Very good. How do you proceed from there? The macrostate is given by how many particles in cell 1, how many in 2, how many in 3, and so on. Then you say the total number of microstates. Number of microstates that are compatible with a given macro state is called the multiplicity. And that we're going to call by the letter W, capital W. And what that is the following. If you have a given macrostate with these populations here given, one possibility is to have, well, you just put particles in each one of these cells according to these numbers. But you can now also go ahead and permute. Suppose you take a particle from cell 1 and you put it in cell 2, and you put a particle from cell 2 in cell 1. When you do that exchange, here you have another microstate that corresponds to exactly the same macrostate. The number of such microstates is called the multiplicity. And the idea is, if you're going to permute the particles, and there are n particles, the number of permutations that you have is n factorial. But of course, when you take a particle that's in cell 1 and you exchange it with another particle that's also in cell 1, that does not contribute to a new distribution. I mean, it's exactly the same microstate. So under those circumstances, you have overcounted here, and so you have to divide by the number of permutations within that microstate. There are m such cells. Oops. So you have to divide by that. So that's the multiplicity. The way one would think about this is, if this is the multiplicity, what is the probability of the macro state? In principle, you can't tell. There is nothing you can do here. Unless you say, what is the probability of every single microstate? Because if you have, so the probability of the macrostate, the probability of a particular distribution of m's is going to be the probability of one microstate multiplied by the total number of microstates. So you can see here that when I say I am in a given macro state, that means I am either in this microstate or that one or that one or that one. It's the sum rule. If I assume that all the microstates are equally likely, let me see. If I have one particle to be placed in these M cells, I can put it here or there or there or there. The probability that it will land in any one of them, if I make it equally likely, is going to be 1 over M. So the probability for a single particle to be in one cell, why is it not writing? There. Sometimes the tablet has a mind of its own. This is for a single particle to land in one cell. If I want to have n particles, the distribution for one particular micro state is going to be 1 over m to the nth power. And then I multiply by w to have the total probability of this particular distribution, distribution of occupation numbers. You can probably appreciate that I have used the product rule to compute this first factor, and I have used the sum rule to add over all the possible microstates. So the assumption that he made, very reasonably, is that this probability is, of course, proportional to the multiplicity. But I want to emphasize there is an postulate of equal a priori probabilities. Each microstate is a priori equally likely. Where does that come from? Whenever you want to assign probabilities, at some point you have to assign the probabilities of those elementary propositions from which you construct everything else. So if I tell you the probability of have a coin and I tell you the probability of heads is 1/3, just on the basis of that, you can figure out the probability of 3 heads in a row followed by 2 tails, or by 3 of one kind and 2 of the other and 5 of the other. You can compute anything you want just using the sum and the product rules. You need always to have this starting point. Otherwise, some starting point. Otherwise, you can't get the whole machine of inference running. And so this is a situation in which what he was doing was assigning the same probability a priori to each cell in phase space. He assumed that the cells were equally likely and of equal volume. So once we have that, he said, well, if I have the probability of each possible distribution, well, let us look for the most probable distribution. So please notice there is no entropy, there is nothing here. He's just saying, look, I start with an assumption of equal a priori probabilities. I calculate what the probability is for a particular distribution. Let me figure out the distribution of W's that makes this a maximum. So this is not a maximum entropy calculation, it is a maximum probability calculation. And how do you proceed from there? What we want to do is, we want to maximize this probability. So the most probable distribution, we want to maximize P. So, or maximize W. Yeah, you can see that this constant that appears here in front, the probability of a single microstate, is independent of the W's. So maximizing over the W's is not affected by this. Maximizing over the W's is the same as maximizing the big W, the multiplicity over the values. So maximize POW subject to the fact that the total number of particles, so this is going over all the cells here from 1 to m, is supposed to be fixed, and also assuming that the total energy, Wn particles with energy En, as you go from 1 to m, this is some given value. So you maximize P or W subject to these constraints, and then the result, we're going to later figure out how to do these maximizations in full glorious detail. The result ended up being that these probabilities were Boltzmann factors. The W divided by the total number, in other words, the fraction of particles in cell n, ended up being proportional to some constant, the energy of the cell. So by doing this calculation, he knew he was in the right, going in the right direction. You maximize the probability, and this distribution of maximum probability is given by the Boltzmann distribution, which is the right answer. Very good. Before we proceed to look at any of those distributions in more detail, let us look at what it means to maximize the multiplicity W. Now remember, let me see. W here includes factorials. So let me box this because this is the crucial expression. This is also supposed to be sort of macroscopic, so the number n is very large. The number W of molecules in cell 1 is also very large. All of these W's are very large. And so the way to figure out what W actually means, to understand what W means, it is convenient to calculate the log of W, which is the log of n factorial, minus the log of Wn factorial summed over all n's. We use the Stirling approximation. And so we have that log W is n log n minus the sum of Wn log W. Oh, wait a minute. Minus n. That's the Stirling approximation for the log of n factorial. Plus, and now we have to subtract the sum over all n. Now we do the Stirling approximation of the second terms there. Wn log Wn minus Wn. All right, so there you have the Stirling approximation. Let's simplify this a fair amount. And what we have here is the following. We're going to simplify this. We're going to use the fact that n is just the sum of the occupation members. So when you see that, when you look at this expression, here you have minus n, and here you have plus the sum of the Wn's. So this n here cancels out those guys there. Furthermore, I can write the n that appears here, I can write it as the sum of Wn's. So let's do that. The sum of the Wn's, that's this n that appears here. Then we have the log of n, right? That's the log of n. And now I'm going to subtract the log of Wn. We're almost there for what our expression is going to look like. Next, I'm going to write this as follows. I'm going to invert n divided by Wn, and I'm going to write it as Wn over n with a minus sign. And furthermore, I'm going to divide by n and multiply by n. Now, why did I do that? Well, the reason I do this is because the quantity that appears here is the frequency, the fraction of the particles that are contained in one particular cell. So what we have here is fraction. And as far as Boltzmann's understanding of probability went, this is the probability. So here we have the log of W is minus n, the sum of the fraction of particles in the cell times the log of the fraction of particles in the cell. So what Boltzmann was doing here then is trying to maximize the log of W subject to constraints on the total number of particles and on the total amount of energy. And as I said before, this is what led to the fraction being the Boltzmann factor, so he knew he was going in the right direction. Now, very good. Let's criticize this now. What's wrong with this? Well, no, in principle, nothing is wrong. It's correct as far as it goes. But we have to be careful here is that the cells are equal volumes, little cells of equal volumes in the one particle phase space. So it's the one particle phase space. Any possibility for and the energies that appear here are the energy of a particle in that cell independently of what all the other particles are doing. So there are no correlations. No interactions between the particles. So this is only good for ideal gases, for free particles. Oops. So you can see the problem here. You can't describe liquids with this or solids or anything of the sort. It's a good idea, but it's not good. Second remark. Clearly, because you're going to be figuring out what the maximum of log W is, remember how this works, we're going to maximize W subject to those constraints, and the probability that emerges is going to be something like this. So you either maximize W or you maximize the log of W, and here we have an expression for the log of W. What you're seeking is the state of equilibrium is the state that has maximum log value. So this suggests that S is proportional to S being the entropy is proportional to the log of, the multiplicity. Good idea. It's actually pretty good. One remark is that the person who, this is the famous Planck's, the famous Boltzmann formula. It is interesting that the person who first wrote this formula, the person who first invented Boltzmann's constant, was not Boltzmann, it was Planck. So the formula that appears in Boltzmann's tombstone is not actually due to Boltzmann, it's due to Planck. History is funny this way. In fact, history is like really funny. You might remember that Planck was trying to describe the statistical mechanics and the thermodynamics of radiation enclosed in an oven, right? Radiation at a certain temperature, radiation in equilibrium, in thermal equilibrium. Planck was trying to do that. At first, he just tried doing thermodynamics. It didn't work. So very, very against his own first instincts, he decided he was going to use Boltzmann's combinatorial techniques. He hated the idea, but he was in such a desperation that he said, oh, what the hell, I'm going to try it. And so the way he proceeded was, he proceeded by dividing phase space for photons dividing phase space in cells and using Boltzmann's methods. So there is a funny sort of like irony in that Boltzmann's constant was really introduced by Planck, not Boltzmann, but the mechanism that led Planck in order to come up with cells in phase space in order to describe statistics of photons and things like that is actually Boltzmann's. He's the guy who came up with the idea of using combinatorics. So you can see that by now the concept of entropy is very much more directly connected to the notion of probability. But as I said, if you wanted to really have correlations, then the much better way to think about this is to think about not the single particle phase space, which is what these N's here do. They label cells in the single particle phase space, but actually to deal with the N particle phase space. And so the way that the generalization goes is to say something like this. S is equal to, I'm going to write this as an integral, and when I do the integral, this is d3x, d3p, and then here I have the formula for the probability of being in x and p, and then the log of x and p, and this is for a single particle. There, something like that. This is the generalization from cells to the continuum. The person who actually generalized this for n particles did this generalization was Gibbs, and he did this in 1902. His book was called The Principles of Statistical Mechanics. In fact, Gibbs was the person who invented the name statistical mechanics. And in that case, the entropy now is going to be, there is a minus sign here. Sorry about that. There is that minus sign there. I forgot that minus sign. Minus and then N. And here I'm going to put the minus. And So this is Boltzmann's entropy, and this is Gibbs' entropy. Minus, and I forgot the K as well, minus K. And here I'm going to write D3 N X D3 N P, and here I'm going to write X1 P1 X N P N, and then multiplied by the log of X1 P1 X N P N. So this is the Gibbs formula that properly takes into account all the interactions between particles. Now I'm pulling a fast one here. If these particles are supposed to be identical, then we may have to divide by an n factorial, the Gibbs factor, and all of those things, right? We'll deal with those later. The point that is much, much more important at this stage is the recognition that there is a huge difference between using the single particle phase space and the n particle phase space. One big difference is that when we write this frequency here as being this fraction, the probability is the fraction of particles that you're going to find in that cell, then the number of particles in that cell ends up being a fairly, I would say, a quantity borrowed from mechanics. It's how many particles you have there, right? And so as you proceed with these calculations and you get to an expression for what the entropy might look like here that involves these probabilities are fairly mechanical objects, and you're sort of justified in thinking of this object here as being a quantity that you have computed from some kind of mechanics. But by the time, so this represents one cell, this is the fraction of particles in that cell. But by the time you have something like this, when you look at this joint probability for the microstate, in which you're actually saying the probability that there is a particle in cell 1, in cell 2, in cell 3, and all that, this is no longer the probability of molecules in a cell. It is the probability that you obtain from having replicas of the system placed in this n particle cell in phase space. Here, the number of copies you have is molecules. A copy of a molecule, another copy of a molecule. How many molecules you have. But here, it no longer works that way. You basically have one system, and this is a probability. You see the problem here. I hope you start appreciating that the moment that you go to the n particle phase space, this F here is no longer the fraction of molecules. At best, you imagine a whole set of replicas of the system, of the macroscopic system, and try to figure out how many replicas are going to be found in one particular microstate, one particular cell in phase space, versus another, versus another, versus another. These objects here reflect something more or less real. These objects here are no longer reflecting anything real. So the way Gibbs said it was something like this. The states of the bodies which we handle are certainly not known to us exactly. What we know about the body can generally be described most accurately and most simply by saying that it is one taken at random from a great number, an ensemble of bodies which are completely described. So each one of the members of this ensemble is completely described. It's a microstate, but you have very many of them. It's also clear that the ensemble, so let me write it like this. F in this case is the fraction of replicas of the system in an ensemble of similarly prepared systems. Each one is completely macroscopic. Now, the ensemble does not exist. This is crucial. It's an invention of Gibbs's imagination. And the thing is, when you talk about a probability as being a fraction, and the only concept of probability you have is probability is a fraction in a large number of trials or in a large number of different, an ensemble of systems, then if the ensemble does not exist, if the number of trials does not exist, you invent it. So the ensemble is imaginary. It is meant to represent the conditions under which the system was prepared, but you do not know what it's essentially just describing the lack of information you have about what is the microstate. Since you do not have other notions of probabilities, you have to invent it. As long as you think of probabilities as frequencies or fractions, you need a quantity, something like this. You need the introduction of ensembles. The moment you realize that probabilities need not be that they can apply to single events as opposed to repeated events, then you no longer need to think of an ensemble. You just think of how you manipulate probabilities. And that's the path that ends up being much more fruitful. Very good. Let me see. What else do I need to say about this? I would like to stop here. What I want to do next is discuss the Shannon approach to entropy, which is a completely separate and separate approach to what an entropy might be. Now, this description that I have produced here leaves us around 1902, and Shannon comes around 1948. So there is an incredible amount of time between the advances of Gibbs and the advances due to Shannon. They were not empty, of course. People did an incredible amount of very useful work between 1902 and 1948. It's almost 50 years. But it was mostly in the direction of applications of this. Once you have this mechanism that you can compute quantities, you can compute probabilities, but maximizing an entropy, subject to constraints, like here are the constraints, subject to constraints, like here at the bottom, you can do an incredible amount of useful work that can be compared to experiment. You have all the applications under control. You can study phase transitions, you can study magnetic systems, you can do a whole lot. So, but it is nevertheless true that what happened between 1902 and 1948 was not particularly useful from the point of view of understanding the very foundations of statistical mechanics. People spent an incredible amount of time attempting to describe the maximization of entropy or the assigning of these probabilities, still relying on ergodic theorems and ergodic theory. And unfortunately, that did not lead anywhere very useful. I'll see you in a while.